Okay guys, let's take a look at today's lesson. We're actually going to be looking at Taylor series over 4 days. We really never spend 4 days on anything, so you can tell by that this is a pretty dense topic. I mean, there's a lot of stuff going on with Taylor series. It's nothing that I can just teach you in one day. We're going to start out looking at a Taylor series. Basically what it is it's a Taylor polynomial just taken to infinity. I mean, that's what a Taylor series is. It's generated by, a Taylor polynomial. And the difference would be is that we actually have a general term. So this is our general term right here. So this general term is what we would use to create each term. So that's a little bit of a change. We know what Taylor polynomials are, and we really didn't deal with a general term for a Taylor polynomial. We just did, whichever third degree polynomial or whatever they asked. Here we have this in addition. We need to do a general term. Now it's rare that they actually ask for the summation. Sometimes they do, but normally what they're going to ask for is a certain number of terms and the general term. You can write a summation if you want to. This is what the summation would look like. The n starting value is what you choose. You would choose whether to start at a 0 or 1. It would be your choice because you're the one writing the general term. Sometimes it's more convenient to start with one or the other. I kind of like starting with 0, but some students really want to start with the 1. It's fine. It's your choice. Okay. So we know, again, as we were talking about when we were talking about Taylor polynomials, if the center is 0, it's called a Maclaurin. And if the center is 0, this would be a Maclaurin series. If it's not, it would be a Taylor series. So we're going to start out kind of slow. We're just going to kind of go from what we knew, which is a Taylor polynomial. And we're going to actually find a Taylor series. We're going to create it from scratch. Sometimes you have to create the Taylor series from scratch. Okay, so we're going to do that first. And it's really just like creating the polynomial, but adding the general term to it. Okay, so let's do that. So it says find a Taylor series for e to the 5x centered at c equals 2. Give the first 4 non-zero terms in the general term. Okay, so let's do that. So we know we start out with a function value, so f of 2. I'm going to go ahead and we're centered at 2. So it would be e to the 5 minus 2 or e to the 10. Okay, so that's where it's our function value. We know we're going to need the first 4 non-zero terms, so we need at least 3 derivatives. If one of the derivatives was 0, we'd have to have another one. It's very specific. It doesn't count 0 as a term. It specifically says the first whatever, however many they want, non-zero terms. So we may have to do more than 3 derivatives, but we'll see how it works. So we'll take the first derivative. So we know the first derivative of e to the 5x, we have to chain that. It would be 5e to the 5x. Then I want to substitute in a 2. So the first derivative at 2, plug a 2 in. I have 5e to the 10th. Okay, so there's my first derivative value at 2. Let's do our second derivative. So our second derivative would be 25e to the 5x. Okay, we're just again doing the chain rule. And our second derivative at 2 would be 25e to the 10th. Okay, is everybody okay? All right, the third derivative would be 125e to the 5x. And our third derivative at 2 would be 125e to the 10th. So I want to pause there, just make sure we're all okay. We're starting this just like we did Taylor polynomials, and we spent 2 days on those, right? So just starting it out, working through. Okay. So now let's go ahead and write the first 4 non-zero terms. Let's go and write them out. I am going to set this equal to e to the 5x because this is what we're representing is e to the 5x. E to the 5x equals. So we're going to write our first term down, which is e to the 10th, plus our second term has to do with the first derivative. Okay, just remember we're centered at 2. So the first derivative was 5e to the 10th. So 5e to the 10th times x minus 2. And this is to the first, so it would be to the first power over 1 factorial, right? And we just normally don't write that. All right, the next term is going to involve our second derivative. So the second derivative was 25e to the 10th times x minus 2 squared over 2 factorial. And you don't, we talked about this before, you don't have to multiply it with the factorial if you don't want to. It'd be fine. So I have 1, 2, 3. I have 3 terms. I need one more. And the next one, my function value at the third derivative is 125 e to the 10th. And that'll be times x minus 2 cubed over 3 factorial plus dot 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 plus. Okay, that's indicating that there are a lot of other terms. A lot of other terms. They just want the general term. This is the norm for us, would be the first however many terms in the general term. So what we're going to have to do is we're going to have to look at the terms that we created, and we're going to have to come up with a formula for them. So what I like to do is I like to do them like one thing at a time. One thing at a time. And so they all have e to the 10th. Right, they all do. So I'm going to put in my formula e to the 10th. Okay, because they all have that. So now I'm going to deal with the 5s and the those numbers, just the regular numbers. So let's see, for the first term it's a 1, and then it's a 5, and then it's a 25, and then it's a 125. So I need to think about something that I could use to represent that pattern. The 1, 5, 25, 125. So 5 to the n is what I chose. So with me choosing 5 to the n, can we tell what n I'm starting at? 0. That was my choice. Did I have to? No. I could have started out at a 1, right? I could have started out at an n of 1. But I started out at an n of 0. So I started at n of 0. So now we need the part with the x minus 2 in it. They all have x minus 2, so let me accept the first one. So x minus 2, and that would be to the n, right? Because if it's to the 0, it would go away to a 1. The denominator, let's look at the denominator. So this has a denominator of 1, that one has 1, then 2, then 3. So n factorial is what I picked, right? Because that would work with an n of 0. So this is our general term. We need to, after it, put plus dot dot dot. Okay, that's what we're putting, plus dot dot dot. We don't have to write the summation. We can if we want to, but it didn't ask us to. The summation would just, basically the summation is where I would say what my n value was. Okay, if we don't write the summation, you don't have to say what your n value is. Now, whoever is looking at your paper should be able to figure it out, right? If you look at my general term, you should be able to figure out that my n value was 0, but I don't have that written anywhere. Where I would write it would be on the summation, which I'm not required to write. So I can just stop there. Okay, so that is our very first Taylor series that we've written. How are we with that? So it's basically just, we are just adding on to the Taylor polynomial a general term. Now that's basically the way to do it by scratch. There are other ways to write series. Okay, sometimes it's not going to be that easy to write a series from scratch. Sometimes it's going to be very complex. So what we have is some basic series that we're going to have to memorize. Okay, so the 3 that we have here, these 3 are the ones you're going to have to memorize because these are the ones that they would expect you to know just by memory. So let's talk about them. So e to the x, these will appear on formula quizzes. Let me explain how they would appear on a formula quiz. What I would say is either one or the other. I guess maybe both. It just depends. Probably one or the other. What are the first 4 non-zero terms of the series e to the x? Then you would write these first 4 terms. Or I might say, what is the general term of the series for e to the x? And then you would write the general term. Now, these have k's in them. I don't really like k's. I like n's better. I guess it's prettier. I don't know. But I want to try to embrace the k's in here. So I chose a book that likes k's, and they use k's for their series, but you don't have to. You can memorize it with a k or memorize it with an n. It doesn't matter to me. Either of those letters is fine. Okay, so that would be an example of how I would ask that to you on a formula quiz. You need to know the series for sine. This is the general terms. Notice that it alternates. Sine and cosine alternate. There's their general term and their first 4 non-zero terms. Okay? Because we know with sine and cosine that they do have terms that are zero, don't they? Because we actually did a Taylor polynomial for sine and cosine. And we saw that a bunch of the terms went away because the derivative was zero. Well, in this case, that's why they say the first four non-zero terms. Now, there are other series that I have given you in the notes. They're like on the last page of the notes that we're going to use in the daily work and other places. If I need you to use a series other than these three, like on a quiz or a test, I would give it to you. Okay? I would give you the series. And that's what they would do on the AP test. If they wanted you to use a series that isn't one of these three, they would give it to you. Okay? So these are the only three that you have to know. The others you just would be given. All right. So let's look at another way that we can create Taylor series, because we're done with that, right? That's the easiest way. Well, sometimes not the easiest, because the derivatives may be just horrendous to do. But let's look at different ways we can create series. Let's go to the second page and see that we can actually create series from other series. Yes, it is possible. It is possible. Okay. So we're not going to be boring and just only, creating from scratch. We can actually use, give ourselves a little boost, use things that are already done to help us create these quicker. Okay. So there are really 5 different techniques that we can use to alter a series that we have memorized or are given. They may give you a series. It's these 5 down here. We can substitute into the series. We can multiply or divide the series by a constant or a variable. We can add or subtract 2 series. We can differentiate or integrate a series. We can recognize it as the sum of geometric power series. We've got all kinds of stuff going on. Now today we're going to focus on these 3. We have 4 days of Taylor series, so as we move on, the day 2, 3, 4, we're going to focus on these 2, but not today. Today we're just going to focus on these, really the more simpler ones to do. So how do we know? We can't always do this. I need to be clear about this, and I don't think I did a good enough job earlier, so I'm being very specific. I'm going to give you an example. We cannot always do this. We cannot always take a series and use it to create another series. It's not always possible. There have to be 2 things that happen for us to be able to do that. So let's look at the 2. What do we need to watch for? When can you do this? Well, there are 2 things we need to watch for. One thing is the center. Are they centered at the same place? You can't just go in and change x to x minus 2. You just can't do that. They need to be centered at the same place. So that's one issue. And what I see is sometimes students want to, do this, like we memorize Maclaurin series. That's what we're memorizing. We're all Maclaurin series. And try to use a Maclaurin series to create a series with a center of 5 or something. It just doesn't normally work that well. Okay, there are rare instances where we could do it, but it normally does not work that well. So we're looking for the center. We want the center to be the same. The second thing that we're looking for is the function value at the center. We're looking for the function value at the center. We want those have to be the same. Because how do we start out a Taylor polynomial or a Taylor series? Don't we start out with a function value? And if they're not the same to begin with, how could we even hope to use one to create another one if they're not even the same at the very first term? Right? So let's look at, I have a question here. So can we use the Maclaurin series for sine x to create the Maclaurin series for this sine? Okay, the first thing we look at is, do they have the same center? Yes, they have the same center. They're both Maclaurin series. They're centered at 0. The second thing that we need to consider is, do they have the same function value at the center? So is sine of 0, is it the same thing as sine of 2 times 0 plus pi over 3? Are those the same thing? They're the same numerical value? No. So no, we can't. No. We cannot use this series to create this one. And I have seen students just kind of do that. We can't, right? We can't. Okay, so we would, if we were asked for this series, we would have to create this from scratch. just like I did the first one that we just did, I would have to do it that way. I'd have to find the derivatives, and then I would have to write out the Taylor polynomial, and I'd have to find the general term and all that. Okay? So we would not be able to use the sine series to change. All right, so I hope that that's clear enough when we can and when we cannot use the series to substitute into. All right, so let's work our first problem. We're asked to find the Maclaurin series for these following two examples. We want to find the first four non-zero terms and the general term. Those are our requirements. Okay, so let's look at this. And I am considering whether I can use the series for sine to create this. First of all, are they centered at the same place? Yes, they're both Maclaurin. If I plugged in the center, 0, into both of those equations, those functions, would I get the same y value? Yes. Yes, I can use sine to create this series. So the first thing I'm going to do is I'm going to write out the series for sine. Okay, so sine is, and you will have this in your memory soon, but probably not yet. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... plus. Now I'm writing out the first four terms of it because they want the first four terms. I mean, I need to at least have written 4 terms here. At least I've written 4 terms to get my first 4 terms. Okay, I'm going to go ahead and write the general term for sine x up here because I think that's going to be helpful for us to create the new one. So the general term is -1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial plus ... Okay, so that's the series that I'm going to use to create sine x squared. Yes. Yes. This. You have to know the first 4 terms in the general term. Yes, for sine x. Okay. So what we're going to do is we're going to use this. We're going to do the technique number 1. We're going to substitute into the series. So think about this sine x squared as basically taking this x and replacing it or putting the x squared inside. We're going to substitute inside of the series. So I have sine of x squared, and that's going to equal. So I'm going to insert x squared where there's an x, and that gives me x squared. I'm going to insert x squared inside of x cubed. If I insert x squared inside of x cubed, what do I get? X to the 6th, right? Because I am inserting it as power to power. So I get x to the 6th over 3 factorial plus. I'm going to insert x squared inside of x to the 5th. That gives me x to the 10th, right? X to the 10th over 5 factorial minus. Again, inserting x squared inside of x to the 7th gives me x to the 14th over 7 factorial plus ... plus. My general term. We just did a fairly simple substitution, right? I'm going to do the same thing in the general term. I'm just going to substitute an x squared where there's an x, and I have my series. I mean, it just was a pretty straightforward. Instead of trying to find the derivatives, all the derivatives of this, which would be fairly complex, right? We'd have to do a power and then a power, then chain and then product, all kinds of stuff. When I can just substitute into the series that I've memorized. So I'm going to use this. It's -1 to the n times, and I'm going to just insert the x squared where the x is. Just going to put that in that place. So that's the 2n plus 1 all over 2n plus 1 factorial plus ... So now I have my first 4 non-zero terms and my general term. Now, you can simplify this if you want to. You can take that and distribute, but there's no need to. I mean, you're just setting yourself up for the possibility of simplifying it incorrectly. And if you simplify it incorrectly, then you would lose the point. So you might as well just leave it. Just leave it like that. And so here are my first 4 non-zero terms and my general term. How is that? Are we okay? Okay. So let's look at the next one. Okay, so this one is more complex. We have a lot of stuff going on here. We have e to the x plus e to the -x over 2. It's like, what? Okay, first of all, let's figure out, can we use e to the x to create this series? So, well, certainly we could use it for that. Could we use it for e to the negative x? Are they centered at the same place? I mean, yeah, it's going to be a Maclaurin. They are. If I put e to the 0, e to the negative 0, is that the same value as e to the 0? Yes, they're the same. So yes, I can do this. Okay, so this is going to take a few steps. Okay, I'm going to have to do several things to this. So I actually need a little bit more room. Are we okay with this? Can I erase right here? Okay. So let's do that. All right, so the first thing I'm going to do is I'm going to copy down the series for e to the x. So e to the x it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus, and you're wondering, well, wow, she's going way more than 4 terms. Well, it's just because I know I'm going to need more, and I'm just going to write them now. If you don't recognize that you need more, you can always go back and add them in, but I know I'm going to need more terms. I'm going to go out to x to the 5th, 5 factorial plus dot 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 plus. And this is too complex. I am not going to write the general term. There's really no need to write the general term for this because I got lots of things going on. Okay, so I'm just going to leave it as the terms. Okay, so now what I want to do is I have e to the x written. Now I want to write e to the negative x. I want to use substitution. So I'm going back to the technique number 1. I'm substituting into the series. So let's write e to the negative x equals. I'm going to replace every x with a negative x, every single one. So I have 1, and then replacing x with a negative x, I have minus x. Okay, I'm going to replace this x with a negative x. It doesn't really do anything, right, because it's x squared. So plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial minus x to the 5th over 5 factorial plus dot dot dot. So basically what happens when I substitute in a negative x is it changes all the terms that have an odd exponent to a subtraction, right? And all the ones with an even exponent, it didn't affect it at all because we know negative 1 squared is 1. Okay, are we okay so far? So I just did substitution. Now this is telling me to add these together, to add them together. So now I'm going to do number 3, add or subtract 2 series. I'm going to add these 2 series together. So e to the x plus e to the negative x is going to be, so let's add them together. So I just add like terms. You know, I can only add the x's with the x's, x squared with the x squared, so forth. So 1 plus 1 is 2. X minus x, well, that's 0. It's gone. Then I have x squared over 2 factorial plus x squared over 2 factorial is 2x squared over 2 factorial. Okay. My x cubed terms are gone. My x to the 4th terms, so I have 2x to the 4th over 4 factorial plus, my x to the 5th terms are gone. And I need 4 terms. I'm down to 3. I have a choice. I can go back and add some more terms, or I can see if I can figure out the pattern here to know what my next term would be. Can we figure out that pattern and to know what the next term would be? Right, so it would be, what, 2x to the 6 over 6 factorial plus dot dot dot. Okay, I've got my 4 terms. Okay, the very last thing, this is being multiplied by a half or divided by 2, however you want to think about it. So that's technique number 2, multiply or divide a series by a constant. Now we haven't done the variable. We can do a variable also. This particular problem, we're just doing a constant. We're multiplying by half or dividing by 2, however you want to consider that. So e to the x plus e to the negative x over 2. So 2 divided by 2 is 1 plus, then I'm going to have x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6 over 6 factorial plus dot 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 plus. Okay, we have our first 4 terms. Now we need to write our general term. Now I'm going to write the general term that I came up with, and I want you to look at it and see if you can figure out what n I am starting at. So let's look at that general term. What n am I starting at? An n of 0. An n of 0. And so my n of 0 would create all those terms. Now just a fun like trivia fact. Maybe some of you already know this. Maybe you recognize this. That is the hyperbolic cosine. Ah, isn't that fun? Hyperbolic cosine? I know you probably haven't had much experience with hyperbolic functions, but that's what that is. Hyperbolic cosine. All right. Okay, guys, so how are we doing? Questions? Yes. Right. No, actually the goal, so it's not. The goal for Taylor polynomials is to approximate something that we don't know how to do. Okay, it's approximating something that we can't do by hand. That's what they're for. Okay, and we're just learning like the baby steps of using them, right? We're just learning how to create them, how to work through them. They actually are used in upper level math quite a bit. Okay, we're just learning the beginnings. Yes.
Do you need to show that the step out of it the same kind of
No, you can just do that by inspection. You can just look and know that that's the same. You don't have to show that. Okay, other questions? Yes. So I needed something. I needed something that would generate x to the 0, x squared, x to the 4th, x to the 6th. And so I knew it needed an x. And then I had to figure out what could I put in the exponent that would generate a 1, a 2, a 4, and a 6. And I came up with 2n. That would generate those two. And in the denominator, I wanted to know what could I do. It looks like 0 factorial, 2 factorial, 4, 6. What could I put there? I know I need an n, right, because it's for the n. And what can I put there to generate those numbers? And I came up with 2n factorial. There are other ways you could do that. In fact, if you remember, for the arithmetic series, you know, this increases by 2 every time. You could go through that formula and get that formula and write the arithmetic series for something that goes from 0 to 2 to 4 to 6. I mean, you could actually use a formula if that was more comfortable than doing it by hand. Okay, you're welcome. Other questions? All right.